minutes. We still have
Yeah,
5
yeah, I
minutes.
know.
I was a bit worried.
Can we
Warm here.
a few minutes? Next year we'll do sabbatical.
That's the plan. Yeah, I want to. I need to.
Yes. So what happened to the students?
Well, we just send them around.
Go ahead at the same time. But she was not interested for those who were my students because we should go to sometimes. One of them was me, not 5, 6, 7.
Yeah. No, I'll be coming back often. Yeah. I won't be away too long. Still around. You were going to Jane.
Also, I apologize if some of the videos have extra stuff in the beginning. I always try to start recording full takes and start tapping. So.
Oh, yes.
I really thought you were going to.
I did test it, so we're good. And you should be good whenever you're ready, sir.
Yeah, I suppose I am supposed to leave at 10 past 4, right? 4:10. Yes, 5 more minutes. Yeah, 3 more minutes. Hi, Uri. Fine. I'm sorry we didn't get the chance to get together, but next time, because my wife was sick. And, well, yeah, some sort of flu. I mean, this usually happens at this, with old people at this. Yeah, Boris was supposed to. Okay, so this is a second talk. However, the talk is, you don't have to be attendance for the first talk. So I hope that will be understood from what I will say today. So the topic is about dynamics and about the persistence. You will not see directly the persistence because you see something which comes out of the persistence. However, I will take the first 1 or 2 minutes to tell you a few words at the very beginning, or a few concepts or terms which might be not familiar for everybody except for mathematicians. First of all, let's say, when I would say computer friendly, I mean about an invariant. I mean by that saying an invariant which can be calculated with arbitrary accuracy by a computer implementable algorithm. Number two, I will use the word of topological closed one form, or for mathematician, one-check cycle. This is something very simple. So let me tell you what this means. This simply means an equivalence class of multi-value maps. So what the multi-value maps is, in my terminology, if I have a space X, a multi-value map will be a collection of continuous map from mu alpha into R with a property that f alpha minus f beta on the intersection is constant. And I said equivalence class by simply means that two such multi-value maps are equivalent if put together remains a multi-value map. For those who are familiar with the concept of manifold and differential calculus on manifold, differential closed one form determined and is determined completely by such a thing. If you put here instead of continuous, you put smooth, because any differential form which is closed is by Poincare lemma is a differential of a form of lower degree, in this case of a function. So the terminology is pretty much the same. So I use the word topological closed one form for this purpose. Another thing which I would use is flow. What a flow means, simply a flow means a one parameter group of homeomorphisms of a topological space. More precisely, if X is a topological flow. Topological space, a flow is a map, a continuous map from L cross X into X, which for any parameter T is in a homeomorphism, but that will follow with the property that mu T, mu Sx equal mu T plus Sx and mu 0 X equal to X. So a trajectory for the flow will be the image. A trajectory will be an image of R cross a point in X. Yes. And I will say that topological closed one form, which is represented by multi-value map, is Lyapunov for the flow. So let's see. Let me put here something else. And the omega, Lyapunov for the flow mu. If any of the f alpha restricted on a non-trivial trajectory, it's, let's say, decreasing, it's strictly decreasing. Of course, that's about non-trivial trajectory, decreasing, or strictly decreasing. So that's all what you have to say. So my talk today will be, let's say, on slides. And I'll try to make clear all the concepts if necessary, although all the concepts are extremely simple. So let me say that I'm starting with the following data. Nice space, which would be called it compact INR. You don't have to know what INR is. I will tell you any compact simplicial complex underlying space is an INR. Any manifold, topological or compact, topological or smooth manifold is an ANR. Any reasonable space in mathematical experience, I mean, it is an ANR. Then I will have generic, okay. Is any way to point?
The laser right there.
Okay, yeah. Yes, where it is a laser pointer? Ah, okay.
It's a little bit hard to see on that screen.
Yeah, okay. So I'll have a flow. I would say a generic flow because most of the flows will be in this class. And I'll have a topological closed one form or one cocycle, which is Lyapunov for the field. But if you are confused by this excessive topological terminology or dynamical terminology, imagine that you have a closed smooth manifold. You have a vector field. You have a differential one form, which happens to be nice. All the zeros are of Morse type. And the vector field satisfies some nice property, some genericity property, which make it the so-called Morse-Mail vector field.
What does, say that word again, that stands for what? Oh,
Morse-Mail,
Oh, I see.
Morse-Mail, stands for Morse-Mail. And of course, I suppose that the form, this one form along the trajectory is strictly negative for non-trivial trajectory. That means Lyapunov in that particular case. So let me add to this fact that if you do have such a topological closed one form, you will have a, which I used to call it check cocycle, one check cocycle. It determines a cohomology class in dimension 1 with real coefficient. In the first case would be in the Durham cohomology in dimension 1, cohomology class C omega. And what is new in this talk versus the talk last time is this cohomology class. If you do have a one-dimensional cohomology class of this type, and if you do have a field kappa, you can get much larger field, what we call K kappa of C. It's an extension of kappa, but actually it's an extension of the ring of Laurent polynomial in a number of variables. It's not important to know what precisely this field is at this time. I might say that if it happens that to be only one variable, this field is exactly the field of Laurent power series. So that will be the ring of Laurent polynomial, and that will be Laurent power series, the field. But it's irrelevant what is at this time. Okay, so this is initial output. What I am interested in, I'm interested in the rest point of the flow of, let's say, of Morse index K. Each rest point will have Morse index. What it is Morse index? Well, you probably know if for a vector field, but if it is for a flow, you look at the so-called the unstable set, the collection of points whose rightward trajectory which depart from the rest point, and the dimension of this topological space is called the Morse. That's Morse index. And I'm interested in something else, in trajectory between rest point. But if I am a person who is interested in experiments, they cannot see all the possible trajectory of rest point, only those which are isolated, which are called visible trajectories. If you are the trajectory between rest points are in a continuous family, they're not visible. And I'm also interested in closed trajectory, again, visible closed trajectory. What I can say from the very beginning, it is the following things, that under the hypothesis which I made of genericity for flow or for Morse-Mail vector field, you say, what happens since the space is compact, the collection of rest point of index K, it is finite, and this cardinality will be denoted by CK. And also, visible trajectory or instanton will exist only between rest point of index k as index point in rest point of index k minus 1. And collecting the information of this what about this instanton can be done with the help of a matrix, but the matrix will have entries in the field, not in the field kappa I started with, but in the extended field kappa of C. And a relevant number is the rank of this matrix. Any matrix of finite number of columns and finite number of rows will have the rank, very precise rank, an integer. So under genericity hypothesis, in both cases, X, the rest points of index K is finite. You do have a matrix which have a precise rank K, and you also, the genericity hypothesis implies that all trajectories are visible, all closed trajectories are very visible. That means are isolated, but even more, but that's irrelevant. In each homotopy class of closed curves, there is only finite many trajectories, but that's not so important for this talk. So, of course, what I would like,
Before you go on,
yes.
rest point.
I'm sorry?
But the index k is equal to, say, 1. Is it correct for me to visualize this as a point where all the vectors come?
No. It's only one direction, only one. The dimension of the points which lie for trajectory, which depart, you can put here co-index, which depart from that point is the topological dimension 1.
So there's only one trajectory?
No, exactly, one trajectory. There is only one trajectory, yes.
And then k
index
is
one.
equal to -1, what happens in that case?
No, the index will be always between, between 0 and n. It is irrelevant, but you see, if it is go back and forth, I said which depart from. There is only one trajectory which departed. If you change the parameter t minus t, will arrive in that particular point. You see, so that's the picture. Yeah. So what I say, the Morse index is a, let's say, topological dimension of the space of points which lie on the trajectory which depart from the point X.
So if I have a manifold with a vector field on it, how?
Much simpler, much simpler. Okay, much simpler. I put here a picture, but let me put here the vector field minus d over dx plus d over dy plus d over dz in dimension 3. This is 0, a rest point. So there is only one direction, this one, let's say, so has index 1. Well, as here, let's say here it's when you put in y and z, and that is. So this is a critical point, the rest point of the vector field of index 1. And yes, and it will be in 3 dimensions, and you have 2 planes or the points on that plane lie on the on trajectory which arrive in the point P. Again, the index will be 1. So it's only one trajectory which depart from this point. Is this trajectory? Well, let's say, no, there are 2. I mean, because t tend to minus infinity, but geometrically it's only 1.
So you wrote down.
Yeah, you see the dimension of this topological space, the unstable set in this case is a full real line except this point, but you might take this point as well. When the dimension of this set is equal to 1, the Morse index is called equal to 1. If the vector field is, if the flow is very ugly, that trajectory which goes into collection of points which are on the trajectory which depart of this thing will form a set. And I'm taking the topological dimension of this set as a Morse index. Is it clear?
Yeah, it's an equivalence class.
Equivalence class of what? Is a topology at points which lie on the trajectories which depart from the rest point.
Okay.
Okay, exactly. Yeah, but it's a smooth case, but that's a question about flows, I consider. So again, what I now? Now I wanted to relate this topology, these dynamical quantities with the topology of underlying space, with very simple aspect of topology. What is the topology in this particular case? Well, if I do have a cohomology class in dimension 1, I do have a sort of sophistication of the homology called Novikov homology. Incidentally, if the cohomology class C will be trivial, will be 0, this field, which I said, is exactly the same field, field kappa. So for C equal to 0, the cohomology class equal to 0, the Novikov homology is a standard homology. Well, the Novikov homology, however, it is a vector space. Well, it's also a vector space over the field kappa, but more important is a vector space over this larger field, like called Novikov Betti number, the dimension of these vector fields over this field. Of course, this for sure is complicated enough to suggest that it's not in a naive way computer friendly. Well, of course, I do have also the standard Betti number, which is a dimension of the underlying topological space. Don't forget, I suppose that the space is nice, it's a compact, it's a nice space. So this dimension is always finite, as it is because of the compacity, the same thing for the other numbers. And here it's a very basic results of the Morse-Novikov theory in this type of situation, but only for very special case of smooth manifold closed to one form. So they relate this quantity, which I just described it to you, in the following way: the number of rest points minus the rank of matrix R minus the rank of matrix R minus 1 equal to the Novikov Betti number. And if the difference between standard Betti number and Novikov Betti number n is different from 0, for sure there exist closed trajectories. Well, you might say how many there are, but not in a very precise way. But I don't want to involve this information at this moment. I can get a lot of information about the multitude of this trajectory. As you can imagine, a priori, that should be a finite number of each homotopy class, which are, so it's a little more complicated to count them. But in any case, it's a very precise, naive statement. If the difference between these Betti numbers, the closed trajectory exists. If the numbers are the rank of that matrices are different from 0, instanton between rest point of index R and R minus 1 exist. Again, a qualitative statement of very interesting practical application. What I will provide, the theory which I'll provide, first of all, extends them from manifolds to arbitrary compact metric space with arbitrary flow, well, generic flows, and closed one form, topological closed one form, which is Lyapunov, and extend this to a much larger situation, but even more. Realize that all these quantities which I'm describing here, this number which I'm describing here, are computer friendly, for reason which would be by no means absolute, or no means very obvious, for sure. That in other ways, if a space is nice, like a simplicial complex, and then you can calculate this number, which gives you information about the dynamics. Okay, so let me say, I will not, at the very beginning, I will not involve all possible topological closed one form, but only a form which is, I called it tame. Well, that is a generic condition. Most of the form will be tame, and a field kappa. Well, I forgot to tell you that just not to be, let's say, intimidated by the terminology, that most of the dynamics in mechanics and in many aspects of physics are so-called local conservative. In other words, do admit a Lyapunov closed one form. And that is when you do have dynamics described by an action, so-called action. That means action can be interpreted as, in the smooth case of a closed one form, in the more general case, a topological closed one form. So what I will provide for you, so what I explain you, I'll explain you what come out from this hypothesis, omega, a tame form, and kappa, a field. I will associate a configuration of points on real line. That means a finite collection of points with multiplicity. Well, I'll tell a little more about configurations. And in fact, I'll consider two types of configuration, and that configuration will be associated for any r equals 0, 1, 2, blah, blah, blah. And the configuration gamma, 0, 1, 2, blah, blah, blah. This configuration will be on the space, on the semi-line, 0, infinity. Again, a collection of points with finite collection of points with multiplicity. That means a configuration. And in fact, it will be very important that the assignment for this configuration will be continuous. I will explain in what sense. And in this case, in general, on the space of configuration, I'll put so-called the collision topology. And if the space appears as a complement of closed subspace in a larger space, there is another topology, bottleneck topology. In fact, which in the case that this in other words, if this subspace would be empty, it's the same as a collision topology. Collision topology is something very intuitive. On the collection of points with multiplicity, one goes to the other and points collide, the multiplicity will be added. Okay, so before I'm continuing to tell you results, let me explain a little bit, few things, elementary things about configuration. Here it is. So if I do have an arbitrary topological space and a subspace y0, configuration of points on y are maps with finite support from y to non-negative integer. In other words, points, finite many points with multiplicity. Point x1, x2, xk, and multiplicity delta x1, delta x2, delta xk.
Sorry, this terminology configuration is standard.
Yeah, okay, certainly standard for, I suppose, for anybody, but not necessary for mathematics. A configuration of points is collection of points, let's say, maybe with some multiplicity. There are points which are identified.
In literature.
Oh, yes. Yeah, yes. Yeah. Oh, well, later mathematical literature, it is certainly. I will not talk about other things that more sort of configuration means mathematically a configuration of points. This simply means in a larger space. What is a collision topology? Well, collision topology is defined by fundamental system of neighborhoods. For example, if I do have a collision like this one, delta, small delta, a neighborhood of this thing will be provided by a collection of disjoint open neighborhoods of, well, instead of x1, x2, xk, I wrote down here by mistake y. So here will be y1, y2, yk. So if I do have delta, a neighborhood, a fundamental neighborhood, will consist of neighborhoods u1, uk of y1, yk, with the following properties. The support of the neighborhood consists of other configuration whose support of delta prime is contained in union of ui, and the sum of the value of delta prime of the elements in ui is delta ui. Let me make a picture because that's considerably simpler to understand. If this is a space y, and I have a point with multiplicity n1, point with multiplicity y1, y2, multiplicity n2. A neighborhood provided by the disjoint open neighborhoods u1 and u2 are all other configuration whose support is contained in u1 union u2. such that the sum of the multiplicity of this one plus of multiplicity of this one plus multiplicity of this one is n1. So if they converge to this point, so the multiplicity will be added. The same thing here. So the topology generated by this fundamental system of neighborhoods is called the collision topology. Incidentally, if you look at the subspace of configuration with exactly k points, that would be the Cartesian product of y with itself k times divided by quotient space by the action of permutation of the symmetric group. Very naive way. But here I consider all possible configuration. So the next one, it is a bottleneck topology. So the bottleneck topology, it's a configuration on the points of y minus y0. This is y. This is y0. So if I do have a configuration of points, these 2 points in y minus y0, a fundamental neighborhood will consist of an open set U1, an open set U2, disjoint, and an open set of y0. So that the support, the configuration in this neighborhood will be all possible configuration with the support are U1 union U2 union V, so that only for U1 and for U2, you have this condition satisfied. In other words, the topology ignores what happens near the subset Y0. This is a so-called the bottleneck topology. It's very familiar for people who are thinking about persistence. It's described in a very different way in standard textbook, but it's essentially the same with what I'm saying to you. Okay, so, well, when I'm thinking about topological closed one form, it's clear that that should have a compact let's say uniform convergence topology. In fact, if you specify a collection of open sets which are contractible, you specify a collection of points, any multi-value map of this thing is uniquely determined by representative, which let's say at that specified point is, let's say, 0. So taking the union of topology uniform convergence for any of these type of open set, you get a nice topology. So at the moment, I am ready to formulate for you the basic theorem, I mean the main theorem. So they said that the summation of the multiplicity of configuration rho is exactly the Novikov-Betti number. And here it's a very stupid writing. It is summation of gamma omega r. So the support, the total support of configuration gamma is a number r. The total support of configuration rho is a Novikov-Betti number. A little bit more important, it is the following. Oh, sorry. It is the third statement. The assignment topological closed one form this configuration delta with a collision topology is continuous. The assignment topology closed one form omega, TC1 form omega, gamma omega in the space of configuration of 0 infinity with bottleneck topology. When you view 0 infinity as closed 0 infinity minus 0 is again continuous. There are a few things which you can see here, which are extremely important to notice. What is the dynamics? What is the flow? Disappear. So in fact, the flow is implicit in omega, which is the topological closed one form, which is the Lyapunov for the vector field. Next, in fact, you got the impression, because what I said, the definition of number R, that at least the cohomology class of the form omega have to be involved. Well, the issue is that we might have two closed topological closed one form which are very close, the cohomology classes are not the same. So in this statement, there is no cohomology class involved. That's extremely important. Because in general, for any topological closed one form, you can construct arbitrarily close to it another one which will represent a different cohomology class. And that would be very important for, let's say, computability of this quantity. So roughly speaking, the rest of my talk at the moment will be to explain for you the definition of the configuration rho and the configuration gamma. Sorry, here it is gamma omega r instead of rho gamma r. It's totally misprint. It's exactly the same thing as this one. So in fact, what will be this computer-friendly object? The computer-friendly object will be this finite collection of points for any R with multiplicity. In other words, this configuration rho. The second configuration, the configuration gamma, final number of points on 0 infinity with multiplicity. So they can be calculated and can be calculated with arbitrary accuracy. And why they can be calculated with arbitrary accuracy? Well, we'll see a little later. It's a little more complicated, by no means obvious. Okay, so in order to describe a little bit this configuration, let me make some background definitions. So let's suppose that you have a continuous map from space U to R, as it is mentioned here. Here it's U, here it's R, and the map, let's say, indicated by the, you can imagine the projection. And for any such a map, you do have the sub-level, and you have an over-level. Sub-level is these things in black, collection of points where the function f is smaller or equal to t, and over-level is collection of points which function is larger or equal to t prime. And you have a closed sub-level and open sub-level, closed over-level and open over-level. Okay, next. To anything like that, you might consider the homology of a sublevel T, rel, open sublevel. Homology of overlevel T, modulo, open overlevel. Dimension of this thing, I have fixed a few data. Well, of course, it can be infinity, or it can be a finite number. And well, let's say there is an immediate concept. The concept of T is a regular value, is h of t equal to 0. Imagine that U would be a manifold, F would be a smooth map, T would be a regular value. The inverse image at the sub-level and over-level would be manifold with boundary. You know that for a manifold with boundary, the homology is the same as for interior of this manifold. So this relative homology is 0, so the dimension is 0, so this dimension is 0. So T is in general called a regular value if this quantity is equal to 0. Very consistent with what you're supposed to know. And its critical value if this does not happen. Well, now it comes a concept. The concept is the tame map. So the tame map, so the map U, the map F, it's tame if U and the level for any T are A and R, are nice spaces. Obviously, if U is a simplicial complex and F is a simplicial map, or even a nice map, certainly the level are compact, are obviously subcomplex, or A and R, compact I and R. Or if this is a manifold, then this would be a Morse function against this thing happens, but not necessary. If F is a smooth function on a manifold, and which is near any point is topologically equivalent to the polynomial, that map will be always, or might be always, tame. So the tameness condition is something very weak, and it is a generic condition. Most of the maps, certainly those who have, we consider in various practical situations, are tame maps. Okay, Let me start with explaining a little bit more. I started with topology a closed one form that provide a cohomology class. And the cohomology class, well, in dimension 1 with real coefficients, is the same thing as an linear map from, or homomorphism from the homology in dimension 1 with integral coefficient in R. So homomorphism from a group, a billion group, which is finite generated to R. So once such a homomorphism is provided and is uniquely provided and uniquely determine a cohomology class in dimension 1 with real coefficient, you do have a group, gamma, the image of this finite generated abelian group into R. The image should have no torsion, should remain finite generated, hence have to be isomorphic with Z plus Z plus Z many times, finitely many times. Okay, well, there is an interpretation of the form omega under this situation. So the group gamma, as appears in this way, determines completely, I'll not explain how, you will believe me, it's not very important. Well, it is important for sure if you want to follow the details. Determines the so-called the principal gamma covering of the space M. That means a space M tilde together with the free action of gamma of M tilde, so that the quotient of this thing, the space of orbits, is exactly M. And so that is depending, this is only a question which associated with the cohomology class omega. But I do have a form omega. The form omega has so-called lifts, continuous map from M tilde to R, so that which are equivariant. Equivariant means if you apply to the action of G on X, you get the map on X, well, plus G, because G, gamma fits subgroup of R acts by translation. And this is not uniquely determined, but almost uniquely in the sense that two such maps associated with omega differ by a constant. So F1 omega and F2 omega, which have this property coming from this situation, F1 minus F2 have to be constant. So up to a constant, they are uniquely determined. And you say by definition that omega is tame if any component of your component of the multi-volume map is tame, or better say, if the map F omega is tame. If F omega is tame, any other representative, let's say F2 omega, will remain tame, satisfies the property which I mentioned for tameness. Okay, so what can I do with these things? Well, there is some sort of very simple math things which I can do. Some of them are very elementary, most of them are very elementary. Here I'm writing the homology, I mean homology with coefficient in the field kappa, which I started with. So first of all, I can consider the image of the sublevel A into M, or of the upper sublevel into homology of M tilde, or the same thing in this case of overlevel in M, respective of open overlevel in M. And once I do have these vector spaces, well, interesting is I don't have to consider, these vector spaces are in general, even if M is compact, and by no means finite dimensional. That would be a really problem. I mean, not a real problem, but it would be very important to note. We do have, for any A and B two real numbers, FRAB is intersection of the image of the sublevel with the image of overlevel. And here for open sublevel, and here for with the open overlevel. And it's almost immediate to see that this subspace is included in this one, the subspace is included in this one, and then I can consider the quotient of these two. What will happen in general, all these spaces which I have mentioned, this one here, are infinite dimension. However, what will happen in general, because of the hypothesis tameness and two other sorts of things, this will be finite dimensional. So that will permit me Well, yes, not necessarily. In any case, this will permit me to define a map from R cross R into non-negative integer possible infinity. The only point that is not a configuration in general, because there's not finite support, at least in general, except in the very special case, omega is actually exact form. So I do have this map of two variables. Okay, well, similarly, I can consider the kernel of the homology of sublevel A into sublevel B, provided that A is strictly smaller than B. And again, of an open sublevel in the level B, in the sublevel B, and of the level A into, let's say, open over level, open over level here. And again, I can observe that there is a natural linear map, obvious linear map from GR smaller AB here, and I'm taking the image. And this is a subgroup, subvector space of this one, and I can form this vector space with the GR. And I can take the dimension of this one, which again will be a map with value in the non-negative integer, possibly infinity. When I'm writing down R2 plus, that is a above diagonal half space, the collection of points x, y, so that x is smaller than y. Right? Okay, so these are two maps. From here, I hope to end up with what I say configuration of the points on the line, respective on a semi-line. Well, there's a number of properties. Some of them are more or less trivialities to verify. Some others are considerably more complicated. 1, 2, 3 claims you that always, if that omega is tame, the value of this map of two variables is finite. Another one, which is also equal, relatively simple to verify, more or less straightforward, that if at the pair of points A, B, that's a different for 0, implies that both A and B are critical values. And the third, that is with respect to the diagonal action of gamma on the plane of AB, this thing is invariant. In other words, gamma AB equals the same as delta of A plus G, B plus G, provided the G is in gamma. Of course, this makes sense to add this type of thing because gamma is always subgroup of R. Less trivial, and well, with a little bit of effort, is that support of this function of two variables with a horizontal, with a vertical line is finite, and horizontal line is finite. However, the support of this thing intersecting with any parallel to the diagonal, to the positive diagonal, I will make a picture and indicate, is everywhere dense, or it's empty. So let me make it precise about this thing. Here is a plane. So support of the map delta intersect with any horizontal line is finite or empty. Support, intersect and support on any vertical line is finite or empty. And support with the parallel to the diagonal it's either everywhere dense or empty. So by no means the support of these maps that's everywhere dense or empty. And the same thing will happen with a second map of two variables. Okay, a similar statement from the function of two variables associated with the map F. Keep in mind that this function of two variables associated with f omega. So for the same omega, I have f1 of omega and f2 of omega. They differ by a constant, of course. Well, one more observation. Here is a diagonal. This is a line of this type, y minus x equal to t, parallel to the main diagonal. And the observation is, first of all, that the support, as I said, of this diagonal, or generalized or parallel to the main diagonal, with the support is either everywhere dense or is empty. Well, in fact, always it's gamma invariant with respect to diagonal action. If you have xy on this line, x plus g, y plus g is also on the same line because of the equation. But the important thing it is the action on the gamma acts on the support, and the number of the collection of orbits of this action. So this set support intersecting with delta divided by gamma, it's finite. So if you, and moreover, by property, which I said, if you have denoted by AB in, in sort of these brackets, the equivalence class with respect to action of gamma, this you can define delta of such equivalence class of delta AB because this quantity is well defined. And because it is support, the collection of orbits is finite, ultimately you get the sum, which is written down here, which is written down here, which is a finite number. 2, if you change f by another one, which represents omega, the result would be the same, from obvious the same reason, the same proposition. And ultimately, this define a map in T, from T in R, into non-negative integer with finite support. This is the delta omega R. I might put here, yeah, I have not put an R. If I put an R as the index over there, that will be each of them, delta omega 0, 1, 2, blah, 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 will be configuration with finite support. Exactly the same definition holds for gamma. Omega R will be defined in the same way, based on the same property. Gamma as a function of t, gamma R as a function of t, is finite, is independent of f, and define a configuration because it has finite support. Okay, so that's a definition. The verification of point 1 and 2 of the theorem, which I said before, it is completely contained in the reference which I put down. They are not very hard. They are ingenious, but elementary. However, to the last point, the continuity is very subtle matter and requires new mathematics. But before of this sort of thing, requires some specification. Let's say the group gamma, I say, can be Zn power n. If n equal to 0, in other words, if the omega is exact, or the cohomology class is equal to 0, well, that's nothing to be said. The group gamma is equal to 0. So the field kappa xi is exactly the same as kappa. If n equal to 1, again, is not a big deal. In this case, always happens if this cohomology class is an image of a cohomology class in dimension 1 with rational coefficient into homology of R, a homo with real coefficient. And if it is non-zero, because I said, if the image non-zero, again, the situation will not be very hard because in this case, always f omega will be a proper map because M was compact. And the critical values will be discrete. Critical value of the map f omega will be discrete. So there are many methods which you might think about determining the map F delta omega. As I'll come back in a minute. However, in the case that n is larger or equal to 2, then what happens, the group gamma, Zn, inside R is everywhere this. Aha, so the situation becomes considerably more complicated. The map which you construct to represent the form omega is never a proper map. And again, the collection of critical value, it's everywhere is critical value. If non-empty, it's everywhere dense. Well, I should say, I use at the very beginning the words of persistency. What's the relation between persistency with this thing? Well, I'm telling you that delta omega AB different from 0 and A smaller or equal to B implies that AB is a barcode for the level persistent, of a zigzag persistent, closed barcode in dimension R for the zigzag persistence. If delta omega AB is different from 0 and A is larger than B, then BA is an open R-1 barcode of the level persistence, or zigzag persistence. If gamma omega R of AB, of course A is more than B, is different from 0, then the interval AB is a closed open barcode in the level or the zigzag persistence. The value at T is calculated from counting this type of barcodes, of course, very many, but fortunately there are finitely many. And they represent, as specified T in the support, length of barcodes, but distributed in a not very obvious way. You say, when they are positive number, represent closed barcodes. When our negative numbers represent open R-1 barcodes, and so far. So that's a relation with persistence. Well, why? What I say, the property T is a continuity. I might have 2 minutes to say something, but I'm not saying almost anything about this one, about the proof, but I will say something about computability. As you have seen, the definition I provide is very far from looking at something which you can implement easily on a computer. However, in the case n equal to 1, one example of such closed one form is a closed one form which comes out by the pullbacking from the map of the space M into the circle. So that bears down, they pulls down to the circle persistence, circle value for circle value map persistence. A number of years ago, a couple of years ago, Tamal Day and I have described an algorithm, explicit algorithm, implementable algorithm to calculate the barcodes for the persistence of angle value maps. So in case n equal to 1, it's okay. Well, next thing, what about n arbitrary n? Well, it is, you say, I have not specified in the theorem, which I prove in part 3 of the theorem specifies the cohomology class. It is not hard to see that any topological closed one form can be arbitrarily closed approximated by a topological closed one form for which gamma will be isomorphic to Z. In other words, which comes essentially from a map into a circle, for which I know algorithms, existent algorithms. So that is the reason of the computability It is a little bit elaborated. If you wanted to do it precisely, what sort of approximation you have to do it. And in fact, the theorem which I put it down here can be much improved, making estimates about, let's say, continuity, but in fact will be about some distances, and with respect to some distance in metric space of topological closed one form and the metric space of configuration with bottleneck topology, so-called the bottleneck distance, which it is. Well, let me, I suppose I should have finished. The point is, to prove point 3, the continuity is a very subtle thing in the sense that we have to go back to some ideas in the measure theory and to reformulate the things in terms of measure. In other words, I have to define a measure, let's say on a real line, which on a segment, it is essentially given by the number of diagonal which intersect in the real line. And each such diagonal will come out by this sort of thing with a contribution of gamma. And I'll put the measure of such a thing as sum of these weights for each such number. In fact, the support of delta omega of gamma omega is on a collection of diagonals. As a diagonal, they are discrete, not the support intersect of the diagonal. And manipulation with this type of measure will prove it, or prove it's a continuity theorem, which is very subtle. I should mention some references for this thing. The idea in the case of n equals 0 or 1 is completely contained in my book or in this paper. Everything which I said from the theorem, and even much more, except the continuity property is not yet is contained in this paper. Continuity will be proven in part 2, which is written but not yet posted. And the computability will be discussed in part 3 of this paper, which is not yet written, or by no, in any way, it's not ready for distribution. So that's all what I have to say. Thank you.
Any questions for Doug?
And you could just back one slide. So I'm just gonna, this is a very naive question. So you said that the case n greater than 1 can be arbitrarily closely approximated by the n equals 1 case.
Yes.
Right? I mean,
no, it's not, yeah, as a level of forms, not a cohomology class, yes.
But I mean, but we know, I mean, the rational cohomology is dense in the real cohomology.
Yeah, but doesn't matter. Yeah, well, that if you want it is like that. The form with rational coefficients, let's say, if you put here for a simplicial complex, let's say, if you wanted the chains with rational coefficient, is dense in the chain with, or the cochain with real coefficient, right? That's exactly what I'm doing. However, the cohomology class of them, if they are very close in the space of cochains, it's not very close at the level of cohomology. And that was a astounding book. It's observation. Initially, the theorem which I had about continuity, about the form in the same cohomology class, that was by no means sufficient to verify the continuity, well, to move to computability. The computability is based exactly on this sort of thing, that with arbitrary accuracy, you can change the form, change the cohomology class of the form, but not much configuration by the theorem to the extent this theorem is proven, but that is already. So that was an aspect which was hardly believable at the beginning for me and for my colleagues I talk with about this matter. This second talk will be also posted. I'll send Fecundo. Those who are interested can find references and Yeah, only the definition and the references which contains all the details.
Can you put up the last reference slide on again?
Okay, sorry. That's paper contains everything which I said for the case n equals 0 and 1, including the dynamics, the story about dynamics and everything like that. The case n larger than 1, strictly larger than 1, larger or equal to 2, is contained in this paper. Everything but, which is, I mean, I suppose maybe have appeared, it's appeared online since, I mean, a couple of months ago. Here, it does not contain the continuity. Contains only the first two parts. The sum of the supports with multiplicity is exactly an orbital of Betti numbers. The sum of the supports of gamma is exactly the rank of the differential in the motion orbital complex, and this type of things. And comments about countability, they are more or less implicit in the part 3 of the theorem is really finished. It's I have to have some more time to check of misspellings and other sort of thing will be posted shortly.
Any more questions or comments for Brian? Well, thanks very much.
Thank you. Thank you very, very much. There is this device. Oh, that's more. Yeah.